Hi, my name is Eduardo and I'm a postdoc at the Australian National University, and today I'm here to talk about memory management for Julia. The title of my presentation is Unbake the Cake and Eat It Too, Flexible and Performant Memory Management for Julia. Following this title, I'd like to start the talk with an analogy. When we think about developing a memory manager for a language, we can imagine that we are baking a cake. As with a cake, there are some decisions that we need to make early on, which will define which cake we get at the end. In terms of memory management, these decisions tend to pose a struggle between flexibility or simplicity and performance. So, for example, we need to decide if we want to implement a simple conservative GC, which should be easier to experiment with early on, or do we want to focus on performance and go precise? Do we want to allow objects to move to reduce fragmentation, or do we go again for a more simplistic approach and assume that objects should not be moved? And then there's a whole new level of decisions. We need to choose which algorithm we want to use, which again will likely affect the overall GC performance. And then, based on these decisions, if we got it right, the result at the end can be a very delicious but very simple cake, or a very sophisticated one. No matter what, the only problem is that once that cake is baked, it's very difficult or almost impossible to go back and unbake it. But now, moving away from the analogy, Julia implements a precise non-moving generation of marks with garbage collector. I won't go into too much detail about how it works, but if you want to know more about it, I recommend going to the Julia documentation webpage. Essentially, the GC performs well, but we have a similar problem here. It's baked into the language, which means that it's harder to change it, to use a different GC strategy, or to perform experiments with it. For that reason, we've been looking into integrating Julia and MMTK. MMTK is an open source, runtime agnostic memory management toolkit, which tries to help finding the balance between performance and flexibility. MMTK has been around for more than 10 years, but has recently been re-implemented in Rust. It has many built-in GC implementations, and has been ported to various VMs, such as OpenJDK, Gixar VM, V8, Ruby, GHC, PyPy, and now Julia. There has been a lot of cool things happening in MMTK itself, such as new GC algorithms being added. For example, Elixir, a low latency, high throughput GC algorithm, which has been just published at PLDI this year. But how to integrate MMTK in Julia? In order to do that, one needs to implement a binding. On one side, you have the VM, which will have everything specific to it, such as just-in-time compilation, concurrency, object initialization, etc. And then, on the other side, you have MMTK core, which is implemented in Rust and contains everything that is GC specific, such as the GC implementation themselves, managing allocation spaces, tracing objects, etc. Then, to implement the binding, you need to implement two different artifacts, which are thin layers connecting the VM and MMTK core. One is an extension of MMTK core itself, which implements its APIs for initializing the GC, allocating and scanning objects, triggering a GC, etc. The other is an extension of the VM itself, in this case Julia, and it's usually implemented in the same language as the VM. It contains code for implementing some of the VM APIs for providing routes, allocating and scanning objects, GC synchronization, etc. We have implemented the MMTK Julia binding and made it available on GitHub on the link on the slide. So if you want to build Julia with MMTK, you can just go there and follow the instructions and try it out. One of the good things is that you only need to implement the binding once. So if you got it right, you can simply select one of the GCs available in MMTK and have it working for your language. It has been shown that this setup has a zero-cost abstraction, so you should be also able to go and obtain good performance. That is, you can have flexibility to experiment with your memory management implementation and don't have to give up performance to do that. In the case of Julia, I can't go into too much detail of how it all works again. But for a limitation on how Julia's root processing works, we are not able to move objects just yet. This means that we are also limited on which types of GCs can be selected in MMTK for Julia. So far, we have tested it with an implementation of the emix garbage collector, but have disabled defragmentation because of this issue. Our main goal has been to try to get this right first, that is, having a correct implementation of Julia's GC using MMTK. In terms of the correctness tests, we are able to pass almost all tests. And as you can see, the number of broken tests that we have are the same ones as you get with the stock Julia. The other tests that fail are tests that are specific to the Julia's GC implementation. So for instance, tests that expect particular function names or that the GC will produce some debug information when it's executed. In terms of performance, we have some initial results. It's worth mentioning that the Julia's GC has been fine-tuned over many years to perform well for Julia programs. So given that we're just starting, we think that the results are very promising. MMTK has a fixed heap size, so we ran the benchmarks with the 4 and 5 gig heap size. The red and green values indicate how much slower or faster, in average, in percentage, each program executed in comparison to stock Julia. As you can see, we are faster in a few benchmarks and slower in others, and we are still in the process of looking into it more carefully to be able to understand the results properly. Well, now that we have a fully functioning implementation of the MMTK Julia binding, we can start experimenting with it. And like I said in the beginning, one of the good things about MMTK is that it should be easier to perform experiments and try things out. So for future work, we have a few things that we are looking forward to try. So for instance, looking at the performance benchmarks themselves and trying to investigate and address the bottlenecks. We want to try other GC strategies, and in particular a copying collector. We want to run more benchmarks, and we also want better integration with Julia and the Julia community. So for more people to use Julia with MMTK. Finally, we also want to experiment with LLVM stack maps and see if they can be used for Julia. That's it. Thank you very much for listening. And again, here's the link to the GitHub project where you can find all the instructions to build Julia with MMTK. And if you have any questions, we are also available on Zulip. Thank you.